All right, this is the third video for class one, third video. And we're going to talk about the classification of fluid flows, maybe talk about control volumes. And then I think we'll make a fourth video for the next part. Let's keep the videos shorter. I don't want to make them as long as they have been. So let's see. I'm going to switch over to my notes here, and let's try to classify certain aspects of fluid flow. Just help to organize stuff. So we have viscous versus inviscid regions of flow, right? So it's really, we're talking about regions where the viscosity matters and where it doesn't matter. And so you can see from this picture, which is much larger over here, right here we have regions. So in the location where we're close to this plate, well, this is the viscous flow region because viscosity matters here in this location. But if you get far enough away from this, and we might call this a boundary layer or something along those lines, we could apply let's say Bernoulli's equation, because it makes an inviscid assumption. We could apply it up here, but we couldn't down in this region right here. That's kind of the big idea behind here, right? So if we the inviscid is far enough away, so viscosity doesn't matter. Viscosity, yeah, doesn't matter. And this is how I would expect that, like, as you would use these notes in class, right? That I might not write this down, but you would write this down. That's what I'm trying to get to here. So that's one way. Okay, so when we're classifying particular things of fluid flows and we want to try to analyze them, we need to start out by deciding whether what we're analyzing is viscous, meaning the viscosity matters, or inviscid, or can it be treated as inviscid because the viscosity it doesn't come into play into the solution. We can also have internal and external flows, right? So as you're here, this is flow inside of a pipe, and this diagram is showing you something called developing versus fully developed, right? So as something enters into the pipe, it before it gets to the pipe, it would have maybe a consistent velocity, but because of the no slip condition, the first molecule and everything is rubbing up against each other. So this becomes so viscosity matters in here in this region, but it doesn't really matter in that region, right? So down in the center is an inviscid kind of thing for a little while until it gets to the fully developed right here, and now viscosity matters all the way along here. And we'll see when we get to pipes, we have to account for viscous actions. But we can also have flow over the outside of a body. So we have internal inside a pipe, external around a body. We had the compressible versus incompressible. Compressible we're really going to do that with gases up to and we know about Mach number, right? Mach 1 is to go the speed of sound. Well, so it's really the Mach number is a dimensionless number because it's the ratio of the speed divided by the speed of sound. But if you get to Mach number, so gases up to less than Mach 0.3, you can treat them as if they are compressible. But if they're moving faster than like 0.3 times the speed of sound, then they start to become a little bit more incompressible, or it is like a transition. And so they start behaving differently. And so that's something we have to really look out for. But we can treat them in a certain way up to this 0.3. Compressible, those are always liquids, right? Liquids are always incompressible, treated as incompressible, even though they might be able to compress ever so just a little tiny bit. Now here's an important one: laminar versus turbulent. So the definition of laminar, you might want to say that it's, or think of it as smooth, right? This is a smooth, and basically it's going to be a slow, right? So a laminar flow is when things are moving very slowly and sort of with a smooth. And we also have a transition. So on the other end of it, we have turbulent, which you could think of as chaotic. All right, so you hear a plane hit turbulence, and so there's a region that it runs into that's all mixed up and rolling around, and this chaotic behavior. And it's usually we can associate this with more of a fast flow, right? And somewhere in between is a transitional right here. So Reynolds number is really the main non-dimensional number that we use to try to determine, is this thing in the range of laminar flow or is it in the range of turbulent flow? And we treat it differently when that happens. And by the way, viscosity can play a part, I guess, in either one of them. Yeah, I was about to say that it was more important than one or the other. Natural flow or unforced versus forced flow. I would actually, in this, you could think that, well, this is just like Mother Nature, right? You have a weather pattern where you have a high pressure region, it moves to a low pressure region, it creates wind, and that's natural, right? Forced flow would be like a fan, right? A fan is accelerating the gas particles, the air, and moving them and forcing them into place. But regardless, the big idea probably want to say is that fluids move from high pressure to low pressure. And it's either just because the pressure already exists or you're causing a pressure differential. Okay. And so we have steady versus unsteady. I think a really good picture was in the right here. So here is like a very fast frame picture of this waterfall. And so if you pay attention to the droplets, or a position that a droplet would pass through or doesn't pass through, is really sort of there's a sort of random behavior. It's not consistent. Whereas here, if you just take it on the average of the motion, you would say this is actually a pretty steady flow, I would think. So. But like the main definition that you would want to kind of think of is that steady occurs when it's consistent with time. Consistent over time. I'll go consistent over time for a given location. Whereas unsteady, it changes with time. Another classification of flows: 1, 2, 3-dimensional flow. Well, all the dimensions are still there, but it's just this is really just describing like if two of the dimensions don't matter, if nothing changes in the two other dimensions, like it'd be up and down or into and out of the page. So it's really just left and right. Like, so if we have a flow that's going this way, we could treat that we could treat that as one-dimensional. It greatly simplifies the problem. So if two dimensions don't matter, or parameters if in the two dimensions don't change or don't affect, use 1D. Right. So if the changes up in that direction don't affect this thing coming left and right, and you can solve along this line, so we'll call that a streamline maybe, then you could treat this as a one-dimensional problem. And even if the thing is like moving like this right here, if the path is going like this right here, you could still treat that as one dimension, right? If you want to. Just being clear that you don't necessarily have to, we're not always talking about X, Y, and Z. But if there's only one direction, that's a single dimension that you can have. Lastly, we have uniform and non-uniform. So a uniform is going to be no change. So if this was consistent over time for a given location, this is consistent with consistent for locations within a region. So we know it's not going to be consistent everywhere in the entire world, but if you kind of like draw like a little imaginary box and you say, what's happening inside this box? Well, like if all of the velocities are the same everywhere inside that box, we could say that it's like a uniform flow, as opposed to like things moving around in different directions. Okay, so here we're going to start off, and so like an introduction to the system and control volume. This is really relevant to something that we'll say later on called Reynolds Transport Theorem, RTT, and we'll cover that several weeks from now. But we define a system and a control volume. The control volume is probably the more important thing, right? So with fluid mechanics, it's useful to us to create a control volume and to see how fluid is flowing into and out of that control volume. The system, however, is sort of the perspective that might be taken maybe in thermodynamics. And we're going to see there's this subtle difference between system and control volume. Now, in the definition in section 1.5, I think it's a little confusing because later on we change and we make a definition that the system, all right, the system is a quantity of mass, or it's a region, right? That's what we're saying in section 1.5, and it's valid because we use this terminology. We call something an open system and a closed system. An open system is one in which mass can go into and out of the system, and a closed system is it's the same amount of mass all the time. Now later on, we change our mind and say, when we say the word bunny ears system, we mean a particular kind of thing of mass. So you can see in this section, they're saying a control volume is just a specific kind of system, right? A system could be either a mass or it could be a region, whereas a control volume is a region. So I guess maybe I don't want to make this more confusing right here. But the control volume is a better way for us. Instead of chasing particles and following individual particles, we just set a little region and say, we're going to take a look at this region, and we're going to say we have these control surfaces that we define around here. And it can be somewhat arbitrary, but we can usually have some amount of reasoning for choosing what the boundaries are for our control volume. And the control volume can change shape, so we can have a moving boundary. We have these control surfaces sometimes that are important because that's where maybe material is coming into the system. All of this comes back down to what we'll be using later on is something called Reynolds Transport Theorem, which is a way of connecting a system point of view to a control volume point of view. These are really the same thing happening. We're just having different points of view. And there's another name for this is the Lagrangian and Eulerian point of view. We'll cover that again, just bringing it to your attention here in class 1, that it's an important kind of idea. But I will mention that I think it's kind of messed up that they use this word system and they mean both a quantity of mass and a control volume, whereas later on what they mean when they say system is they only mean a specific amount of mass, like we would follow like a chunk of mass and have it moving along. and it might pass through a control volume. And we might need to make a connection between the system perspective and the control volume perspective, and that's something done with Reynolds transport theorem. And I'm at my 15-minute self-imposed limit, so we're going to go to video 4.